In this segment, we're going to look at exponential growth and decay models. Well, actually, we're just going to do the growth in this one, but they both follow pretty much the same pattern. You're going to have P of t equals P sub 0 e to the kt. Now, the P could be a different variable. It could be an F, it could be a C, it could be different things. In this case, if I want to represent population, I would usually use a P. All right, so what's the P sub 0? That's the population or amount of whatever at time 0. It's the initial amount. The P of t, the answer over here on the left, that's going to be our population or amount at a given time t. So P of 10 would be at time t equals 10 minutes, 10 years, whatever the case might be. And the t, of course, is time, and the units can vary, so watch your problems. K is this little exponent up here. That's going to be our growth or decay rate, and it's a percentage changed into a decimal. If K is positive, this exponent's positive, then we are going to have growth. If this exponent K is negative, we will have decay. Let's look at a growth problem. Under ideal conditions, a population of rabbits has exponential growth rate of 11.7% per day. We want to consider an initial population of 100 rabbits. Okay, well, if they've given me the growth rate here, they're really giving me a K. They're telling me it's growth, so I know it's positive, and I just change it to a decimal. They're also telling me the initial population, which is the P sub 0. Plugging both of those in, we get this equation, P of t equals 100 e to the 0.117t. So there's our function. Now, can we use that to make some predictions? We want to know what would the population be after 3 days. So our t is 3. We're just going to plug it in up here. Now, P of 3 equals 100 e raised to the 0.1173. If I want to put this in my calculator, I do kind of have to be careful. I'm going to go ahead and I'm going to put 100, and then my e is right above that ln button, so second, and then my e. It already opens a parenthesis, so I'm going to put my entire exponent in here and then close the parenthesis. So the 0.117 times the 3 and then close your parenthesis. Be very, very careful there. So it's about 142 rabbits in just 3 days. Now, a little bit more interesting question is going to be, when will we get a certain number of rabbits? So if we want to know the time required to reach 200 rabbits, that could also be called the doubling time since we started with 100, what we're going to do is say our answer here, the P of t is 200, and that equals 100 e to the 0.117t. Now I could graph this side on the left as y1, this side as y2, and then try to find the intersection point. But let's go ahead and try solving it algebraically so we don't have to mess around with the window and figure out what the best window is. Algebraically, because it's an exponential equation, I want to isolate this e part here, so I divide both sides by 100, get 2 equals the e to the 0.117t. Then we're taking the natural log of both sides, so put your ln in on both sides. That allows us to use the power rule, and that means the exponent comes out front of the log over on the right, and we get ln of 2 equals 0.117t ln of e. But ln of e always reduces to 1 because it's the power I put on e to get e. So the only thing I have to do to solve for t is divide by 0.117, and I do that on both sides. I get about 5.9 days. So in less than 1 week, our rabbits have doubled.